Hi guys, welcome back. In this example, I want to talk about how you can model a mass spring damper in a vertical direction. So at first, we're gonna work with the origin of our coordinate system measured from the free length of the spring. Then we're gonna change the origin to the static equilibrium point and see what we can achieve with this shift in the coordinate system. Okay? So let's get started. I'm going to first list the elements in the system, just like the previous examples. So let's go after the elements. First, inertia, stiffness, friction. My sources, and the number of ODEs. In this problem, you notice that I have only one mass, so my inertia element is mass. The stiffness is basically my spring. My friction element is my viscose damper. In this problem, there is no external force applied, so I would not have any source. And the number of ODEs for this problem is only one. Why? Because naively speaking, we have only one mass. Okay, and we mentioned that we're gonna fix this at the end of these series. Okay, now let's go to our 4-step approach at this point, okay, and derive that only one ODE. So step one is selecting my coordinate system. So select our coordinate system. Okay. If you guys remember, for selecting a coordinate system, you need two things. First thing was the origin for that coordinate system, or the reference. The second one was the positive direction. In this problem, let's select the origin of the coordinate system as free length of the spring. What is the free length of the spring? Basically, it's the length of the spring when the spring is undefected. And also, for the positive direction, I'm going to work with the same downward positive direction that's given to me. Okay? Nice. Step two, we are going to isolate the body, isolate the inertia element. Okay? Isolate the inertia element. What do we mean by isolating? It means that grab the inertia element, disconnect it from the system, and throw it on a piece of paper. So I'm going to grab it, I'm going to disconnect it, and I'm going to throw it on a piece of paper. And if you guys see, I'm going to show the coordinate system on top of this guy. So I can go now to the step 3, which is a free body diagram. Yes? In free body diagram, if you remember, we went after few, CSR. Just to refresh our memory one more time, F was friction force, E was external, W was weight, contact is shown with C, spring is S, and R is rope. So we go after this sequence of forces. First of all, do I have a friction force in the system? Yes, I do. I have the bearing. If you guys look at this bearing, only one side of this bearing moves, the other side is clamped to the wall. So this is an easy model. Yes? The magnitude of this friction force is bx dot, which x dot is the velocity at the free end, okay? And the direction is opposing the direction of motion. If you assume that your box is going in the positive x direction, this is going to be negative x direction. Okay. Next one. So I'm going to cross out the friction. Next one is the external force. If you guys notice, we do not have any external force. So I'm going to cross this one out too. The next one is the weight. Note that weight is always applied at the center of gravity, pointing downward. So this is my weight. I'm done with this one as well. I do not have any contact in this system. It's hanging in the air. Yeah. The next one is the spring. You have one spring here. So note that again, one side of this spring is clamped to the wall, the other end moves. Yes. So again, this one is an easy model. Since one side moves, okay, we say that, okay, this is going to be K multiplied by the displacement of that side. The important thing is the direction of this force. Imagine yourself as the spring and you're hanging from the ceiling. If somebody pushes your legs down, are you going to be stretched or are you going to be compressed? Well, I think you are going to be stretched, yes? So when you're stretched, you're going to pull or push back? You're going to pull, yes? So if you pull the mass towards yourself, this is going to be the direction of the spring force. Okay, so spring is gone. We do not have any rope in the problem. The free body diagram is complete. At this point, you can safely navigate towards step 4, which is the equation of motion. Okay. For the equation of motion, what we're going to do is we're going to write down the Newton's second law along x direction. Okay. Look at your free body diagram. How many forces do you see? I see 1, 2, and 3. Correct. Now, look at W. W is in fact in the positive x direction. However, Bx dot and Kx are pointing towards negative x direction. Okay, so we bring them with their signs. W is positive. Those two are negative. Good? Okay. Nice. And this is equal to mx double dot. So let's move around some things here. Let's bring the dynamic terms on one side and keep the static terms on one side. Okay. So you see that I would have W equals to mx double dot plus bx dot plus kx. Before boxing this equation, you need to check for the signs. You see that I have only one family, and that's family of x. Within family of x, I have 3 members: x, x dot, x double dot. Yes? And the sign of all of these guys is positive. There is no sign mismatches within the members of family x. So I can safely box this equation and report this equation as my final answer. If you look at this system, you see that this is a linear time invariant system. And the order of the system is the maximum order of the derivative here, which is second order. Okay. I think we are done with this model. There's just one thing that it bothers me a little bit. What is it? W. It's a static force. Yes? And I want to see if there is any way that I can get rid of W. Okay? And actually, there is a nice way to get rid of W. How? Note that in this model, we started the origin here, okay, from the free length of the spring. So it sounds like if somebody was here looking at this system downward, and the person was at the free length of the spring, he was gonna or she was gonna measure the distance of mass from the free length of the spring. But who knows what's the free length of the spring? Probably the only person who knows is the person who bought that spring and put it in the system. Is there a better reference for this system? Well, I think it is. I would look at the static equilibrium point. Okay, so I would let the mass, spring, and damper to hang for a while, okay, and become at rest. Then probably the mass is going to come at rest over here. Then I would look at the system from that point. We call it as static equilibrium point. Note that, guys, there would be a difference d between the free length of the spring and the static equilibrium point. And we want to see how can we use this d to model the system again in a better and more efficient way. Okay, so let's go ahead and do that. Okay, so I'm going to assume that x eq, which is basically the ed, basically the d value, okay, is the place that I'm going to become at static equilibrium. The system is going to go to rest at that point. Okay. And what I'm going to do is I'm going to put this d into the dynamics that I have. Yes. Okay. So if you substitute d, or a static equilibrium point, in the dynamics that you have, let's call this equation as equation smiley. You will get what? You will get W equals to M d double dot plus B d dot plus K d. The only thing that I did was I just substitute X dot, and X double dot as D dot, and D double dot. Okay? So you guys tell me, D is a constant number, yes? Is a constant number. And if D is a constant number, what is going to be the time derivative of D? Well, if D is a constant number, the time derivative of D would be 0. What is going to be the second time derivative of D? Again, if D is constant number, the second time derivative of D would be also 0. Yes? Okay. With this, let's go back to the dynamics and see what is going to be the value for D double dot and what's going to be the value for D dot. You guys agree that it's going to be 0. Yes? Okay. So from here, I can have a value. I can solve this equation for D. Okay. And I can have a value for this guy and say that, okay, my D is in fact W over K, which means that if you have the W and you have the stiffness of your spring, you can easily find the distance from the free length of the spring and the static equilibrium point from this equation. Okay. So now let's go ahead and shift our coordinate system. Yes. So from mathematics, if you guys remember, if you want to shift a coordinate system with the D value along the direction of positive X, then your second coordinate system, let's say it's Z, okay, this is gonna be X minus D. Yes? Okay, so what does it mean? It means that if at the beginning you're the person who is sitting at the free length of the spring and sees the mass or measures the mass. And if I am the person that sits at the static equilibrium point and measures the distance of the mass, okay, I am always seeing the distance d value less than u. Yes. So for instance, if you say that, okay, the mass is at x equal to 10 and d is basically 2 meters, okay, so let's say this is 10 meters and this is 2 meters, the person who sits at the static equilibrium point sees the distance of the mass 2 meters less than a person who is sitting at the static equilibrium point, okay. So that person is in fact seeing the mass 10 minus 2, which is 8 meters away. Okay, so this is basically the main concept. Yes. Okay. So let me get rid of these calculations, okay, and go back to the problem. This is my new coordinate system or new origin, okay, and this is my old one. Okay. Okay. Now, let's take some derivatives, okay, and see what's going on. First of all, I'm going to solve this equation for x, okay? So x is in fact equals to z plus d, okay? And I'm going to take the derivative x dot, okay? It's going to be z dot plus d dot, which you guys already know that d dot is in fact 0 since d is a constant number. So x dot is equal to z dot. And similarly, my x double dot is z double dot plus d double dot. Since d double dot is 0, my x double dot is in fact z double dot. Okay, so look at this. What I'm going to do is I'm going to substitute these three values for x, x dot, and x double dot in equation smiley, yeah, which is here. Okay, so substitute x, x dot, and x double dot from, let's say this is equation 1, from equation 1 into a smiley. What do you get? Let me rewrite the equation smiley one more time. W equals to m x double dot plus b x dot plus k x. Yes? So instead of x double dot, look at here, I can put z double dot. So good. This is going to be z double dot. Instead of x dot, I can put from 1, I can put z dot. Yes? So this is going to be z dot. Instead of x, I can put z plus d. So this is going to be z plus d. Okay? Now look at this. I'm going to distribute this k here and here. Okay? And I'm going to rewrite this equation. Okay? So this is going to be w equals to m z double dot plus b z dot plus k z plus k the value d. Yeah? So can you guys see it now? Well, it might not be clear, but look at this. This equation that we had for the static equilibrium point, okay, and this equation which was for the w. You said the value of the w was in fact equals to kd, yes? So this is in fact on the right hand side, kd is equal to the w on the left hand side. So you can safely cancel out these two terms. So what do you end up with? You will end up with 0 equals to m z double dot plus b z dot plus k z. Okay? Let's do a quick sanity check for this. How many families do you have here? Well, you have only one family. That's the family of z. Okay? And within that family, you have three members, z, z dot, and z double dot. And you guys see that there are no sign mismatches within the family, yes, within the members of the family. So you can safely box this equation. Okay. Now, if you compare, let me call this equation as equation cyclope. If you compare equation Smiley and equation cyclope, okay, you see that both equations describe the dynamics of the same system. One equation, which is equation Smiley, has W in the dynamics, okay, and X. The other one does not have W and it has Z, which means that by a simple change of the coordinate system, the origin of my coordinate system, by shifting the coordinate system from the free lengths of the spring to the static equilibrium point, I was able to somehow neglect W in my formulation. Okay? So here is what I want you guys to do from now on. Anytime you have a vertical motion with the springs and dampers and those kind of things, assume that the origin of your coordinate system is started from the static equilibrium and not the free lengths of the spring. With this assumption, you can neglect W directly in your free body diagram, okay? And basically solve for the dynamics of the system. If you find this video helpful, make sure to subscribe to the channel for more physics-based modeling and follow the full series as we build our way towards intelligent control and autonomous systems. Thank you.